Hello everyone, my name is Yejun Liu from Shanghai Jiao Tong University. Today I will present our work, Divide, Conquer, and Aggregate, Asymmetric Experts for Class-Imbalanced, Semi-Supervised Medical Image Segmentation, accepted by CVPR 2026. As we can see from Fig 1, multi-organ datasets such as Synapse and AMOS are highly imbalanced. Large organs dominate the voxel occupancy, while small organs occupy only a tiny proportion. Existing SSMIS methods mainly focus on improving pseudo-label quality, but most of them still use a single decoder to predict all classes. This makes the decoder biased toward majority organs and limits its ability to segment tail organs. So the key limitation is that pseudo-label debiasing alone is not enough when the decoder architecture itself is not scale-aware. As shown in Fig 2, although the exact class rankings fluctuate under different labeled ratios, the overall stratification remains stable. Large organs are usually still large, and tiny organs remain tail classes. This indicates that class imbalance in multi-organ segmentation is not random noise, but is closely related to anatomical scale priors. Based on this observation, we divide organs into head, medium, and tail groups and design category-specific decoders for different segmentation difficulties. In short, stable anatomical stratification naturally motivates a divide and conquer framework. Although exact rankings vary across labeled ratios, large organs and tiny organs remain relatively stable. This suggests that class imbalance is not random noise, but reflects anatomical scale priors. This slide summarizes our main idea: divide, conquer, and aggregate. First, in the divide stage, we use log gap analysis to partition foreground organs into head, medium, and tail groups in a data-driven way. Second, in the conquer stage, we train 3 asymmetric expert decoders with label split supervision, so each expert specializes in its own organ group and avoids interference from other classes. Third, in the aggregate stage, we use logit stitching to generate expert-fused pseudo-labels, and DFAM to dynamically aggregate expert features. Overall, instead of forcing one decoder to handle all organ scales, DCA assigns scale-aware experts and aggregates their complementary strengths. Fig 3 shows the overall pipeline of our divide, conquer, and aggregate framework, or DCA. The key motivation is that class-imbalanced multi-organ segmentation is difficult for a single decoder, because large and small organs have very different scales and visual patterns. DCA addresses this problem in 3 steps. First, we divide foreground organs into head, medium, and tail groups using log gap analysis. Second, we conquer the imbalance task with 3 asymmetric expert decoders, each specialized for one organ group. Finally, we aggregate their knowledge through a dynamic aggregation decoder to produce the final segmentation. In this way, DCA reduces majority class dominance while still maintaining a unified prediction. The first stage is divide. We start by computing the voxel count of each foreground organ from the labeled set, and then normalize it by the total foreground voxel count. This gives the foreground occupancy ratio for each class. Instead of using handcrafted thresholds, we sort all class proportions and compute the logarithmic gap between adjacent classes. A large log gap indicates a natural boundary between organ groups. We use the 2 most prominent gaps to split organs into head, medium, and tail sets. These sets are fixed during training and guide both the expert decoder design and the loss computation. The main advantage is that this partition is data-driven, parameter-free, and consistent with anatomical scale differences. The second stage is conquer. After the shared encoder extracts features, the features are sent to 3 expert decoders: the head expert, medium expert, and tail expert. The head expert uses dilated convolutions and fewer layers, which helps capture large organs with broader context. The medium expert follows the standard VNet decoder design. The tail expert uses more convolutional layers to better capture small and detailed structures. To enforce specialization, we split the ground truth label according to the head, medium, and tail sets. For each expert, classes outside its assigned group are remapped to background. The supervised loss is then computed separately for each expert and summed together. This allows each decoder to focus on a smaller and more balanced segmentation subtask. For unlabeled data, we generate pseudo-labels using logit stitching. Instead of averaging the three expert predictions, we directly stitch their raw logits according to their assigned class groups. For example, head class logits are taken from the head expert, medium class logits from the medium expert, and tail class logits from the tail expert. The background channel is shared by all experts, so we average the three background logits to obtain a robust consensus. Finally, the fused pseudo-label is obtained by taking the argmax over the stitched logits. This design preserves expert specialization and avoids conflicts that may occur when averaging softmax predictions from experts trained for different class groups. The final stage is aggregate. The aggregation decoder uses the Dynamic Feature Aggregation Module, or DFAM, at each decoding stage. DFAM receives features from the aggregation stream and same-level features from the three expert decoders. First, expert features are projected with 1x1x1 convolutions and concatenated. Then, a lightweight gate generator produces three spatial attention maps through a channel-wise softmax. These attention maps sum to 1 at each voxel, enabling voxel-wise competition among the experts. The final expert feature is obtained by attention-weighted summation, and then fused with the aggregation stream through residual addition. The aggregation decoder is supervised by the stitched pseudo-labels on unlabeled data. The final objective combines the supervised expert loss and the unsupervised aggregation loss. Overall, DFAM allows the model to dynamically select useful expert priors and generate more balanced final predictions. Tab 1 shows the quantitative results on the Synapse dataset with 20% labeled data. Compared with both general SSMIS methods and class-imbalance-oriented methods, DCA achieves the best average dice score of 73.20. It outperforms the second-best method, GA, by 4.77 percentage points. Importantly, DCA ranks in the top 3 across all 13 organs, showing balanced performance rather than improving only a few large organs. The qualitative results in Fig 5 also show that our method produces fewer under-segmentation errors and better separates small or overlapping organs, especially in challenging tail class regions. Tab 2 presents the quantitative results on the AMOS dataset with 5% labeled data. AMOS is larger and more challenging than Synapse, with 15 foreground organs. DCA again achieves the best performance with an average dice score of 69.90. It outperforms the second-best method, GA, by 6.39 percentage points and achieves the highest dice score across all organs. The TSNE visualization and Fig 6 further shows that DCA learns more compact intraclass features and clearer interclass separation, which supports its effectiveness for multi-organ segmentation under class imbalance. Tab 3 analyzes the contribution of each main component. Starting from the baseline, adding 3 expert decoders improves average dice by 7.46 points. This shows that expert specialization helps relieve the burden of a single decoder. Then adding log gap analysis and label splitting brings another 14.51 point improvement, confirming that data-driven category division is crucial for effective expert learning. Finally, adding DFAM gives a further 3.31 point gain by dynamically aggregating expert priors. The split strategy ablation in Tab 4 also shows that log gap analysis is more stable and effective than uniform division or fixed threshold division. For the decoder design, using asymmetric experts achieves the best performance. The deeper tail decoder improves small organ detail extraction, while the dilated head decoder helps capture larger organ context. The category-wise performance figure further confirms that different organ groups benefit from different decoder designs. For aggregation, the feature map comparison shows that DFAM activates both head class and tail class regions more effectively than average fusion or simple concatenation. Overall, these ablations show that each part of divide, conquer, and aggregate contributes to stronger and more balanced segmentation. To conclude, DCA improves class-imbalanced semi-supervised medical image segmentation by reducing the dominance of majority organs. Through expert specialization, the model learns more balanced representations for organs at different scales. With dynamic aggregation, DCA further combines complementary expert knowledge to produce robust final predictions. Overall, our method achieves superior results on synapse and AMOS, with especially clear gains on tail class organs. Thank you for your attention. If you are interested in more details, please feel free to scan the QR code for our project page and code. I would be happy to take any questions.